Last time you were saying chronological evolution, and now it's sort of more doing subjects, just it's law.
I think that might be a good primer for this course. This would be-
Yeah, well, let's see, yeah.
All right, we're underway. Good morning.
Good morning.
Before I say the normal greeting, I want to read you something. I call it opening statement. I want to set the tone for this meeting. It's not a lecture.
Thank you.
It's a conversation that we will have. I just started before you, so I have accumulated some more information than you currently have. By the end, you will know everything. So I'm going to read this to you because I thought very carefully about what this is. The universe is unimaginably large and complex. It contains a vast array of physical processes, only a few of which we understand, we think. Understanding the behavior of the universe depends on knowing how the big things, like galaxies, behave. But it also depends on how the smallest things, like atoms, interact, since the small things dictate how the big things evolve. Given this information, one would be justified in saying, how can we ever make any progress in understanding the structure and dynamics of the universe? But, despite these challenges, it turns out we know a great deal. We have numerous independent confirmations of a variety of topics. We have built machines on Earth and in space that allow us to compare theory and experiment. You and I are here to explore what is known and what we know that we do not know. We will guess about what we may never know. I will point out where there are problems with our knowledge, but always keep in mind that virtually every scientific theory eventually gets overturned and improved. And our theories are our theories the way nature behaves? And we can confidently say no. Nature does not have a giant computer where they calculate how atoms should move and so forth. There's something we will never understand about why the universe behaves the way it does. I'm paraphrasing this a little bit. We have theories about all sorts of things, like how gravity works, which allows us to go to the planets with probes and fly around Mars and so forth, and that all works. Is that what nature is doing? No. Something else, something about the geometry of the universe we live in, something we do not understand, may never understand, dictates how things behave. We just happen to find a way to manage that using the mathematical tools at our disposal. We have made progress, but this enterprise will take forever. And for that to happen, society has to be willing to divert resources to the science underlying our understanding of cosmology. And I'm hoping that as this course unfolds, you will have the tools to discuss these topics with your neighbors, your family, and the community at large, and become an advocate for continuing this enterprise, which has existed for thousands of years. I like this quote: if you want to build a ship, don't drum up people to collect wood and don't assign tasks at work, but rather teach them to long for the endless immensity of the sea. And that's essentially what we want to do in these meetings. So we're going to start in a second, but I want to encourage conversation, questions, and so forth. I hope that questions that come to mind between now and our next meeting, you'll bring to the next meeting so we can start every session with questions that you may have about things I've said or the ideas that we've talked about. So today, I'll show you the structure of what we're going to discuss. If you brought questions for today's meeting, then we can talk about those. I'll show you what we're typically going to do in a lecture. And I shouldn't, the word lecture bothers me. This is a conversation. So I want your participation. I'm not the only one who should be talking. So we'll start every session with talking about questions you may have. And we'll do that today as well. Some of those questions I won't be able to answer immediately. I'll have to do some study. I just had a conversation with John about this. I'm going to learn as much as you do because people are going to ask me questions that I don't currently know the answer to. And I'll have to do some homework. Most of what I'm going to present to you involves videos and images. I might show you one or two equations in the form of art. So if you go see a modern art exhibit, we don't always know what the artist had in mind, but there's something graceful about what they present. And the equations that pertain here are that way too. So we'll look at some of them just to see what they look like. We'll have 2 breaks, unless people want more, that's fine. The idea is to gather an understanding of the concepts. Occasionally we'll drill down and get into some of the details. But the idea is when you leave here, conceptually you'll have a view of what is currently known. And so I'm going to interrupt myself and say, the key thing I want to give to you is what is currently happening in the study of cosmology. I mean, you can read books, and probably all of you have. Brian Greene and Neil Tyson and a variety of other people produce a fountain of books. You can't keep up. But it takes years to write a book, and in those years, things change. And I will introduce you to some current issues, one of which just came up this week. We won't do it today, but things are happening all the time. So I want you to know what is on the table in the scientific community on the topic of cosmology. No homework, but I have available things for you to look at if you want to do some things at home. So I just said this. We're going to focus on what's happened in the last 40 years. There's been a revolution in our understanding of the cosmos in the last 40 years, but things are happening on a weekly basis. So when we get done, we'll already be behind. I am videoing this screen. So if you don't want to appear in the video, walk around or something. And it includes, I'm recording audio as well. So if you're concerned about that, let me know. I have a little peeve here about saying the Earth. I will do it occasionally. What I mean is we never say the Mars. We're going to go explore the Mars. Mars is the name of the planet. Earth is the name of our planet. So I'd like to do my little part to clarify that in terms of English. So I try to avoid saying the Earth. If we're talking about the planet, I will say Earth. We'll use this abbreviation GYR for billions of years, because in some of the material I'll show you, the professionals use this terminology, and you will see some things produced by professional astrophysicists and cosmologists. So understand that means billions. That's the European definition. So today we're going to talk about the big picture. I'll try to get your arms completely around the universe and see the things that matter. The next time we meet, we'll focus the entire session on the early universe. And by early, I mean something like the first 3 to 5 minutes of the universe. And how we think we understand what happened, because the residue of that is us. We can look at the composition of the current cosmos to determine what dynamics were underway in the early universe, because that's when most of the materials that we deal with were produced. Then we'll talk about something a little more technical, and that is the earliest light that we can detect from the universe. This is light born very soon after the universe began. It's all around us. In the old days, people had TVs with an antenna, also an aerial, and if you tuned the TV in between channels, it was just, fuzzy noise on the screen. About 20% of that is radiation from the earliest days of the universe. It's called the cosmic microwave background. So we'll spend a session on that. We will talk about this contrarian statement. Everybody's familiar with gravity. Einstein showed us that the concept of gravity, that objects are attracted. If I drop my canister here, it will head toward the center of Earth. That's not what's really happening. So we'll invest some time talking about that because that's an important product of Einstein's invention of a theory, an alternate theory of gravity, which we now know is correct. We'll spend a whole session on black holes, including what happens to astronauts who venture near or into black holes. There are a wide variety of new technologies being put together to study the universe. You may have seen news items about gravitational wave detection. This is a new window on the cosmos and has proved very successful in solving some pretty basic questions, and it's only been in use for 2 years. So we'll talk about that and other types of observational techniques in space on the ground. Because we're doing a survey up to this, through the first 6 conversations, we'll go back in the 7th one and do some deep drilling to fill in some gaps. Because I don't want to show you everything at once, it would be too much detail. But by the time we get to the 7th meeting, you'll have the background to understand the details I'll present there. And along the way, we're going to accumulate questions from you, my partners in this enterprise, as well as the unanswered questions that cosmologists are wrestling with right now, such as I mentioned, something happened this week we will talk about. So the questions will be accumulated for the last session, and I hope you'll make some input toward that. I already have a bunch of things in mind to talk about. So I should say, this is not the first time I've taught this kind of thing. I taught at Colorado State University in the fall semester, similar audience, similar age, and probably the distribution of backgrounds from a technical point of view. And I learned a great deal presenting that class at CSU. I do not live in Fort Collins, so driving up there from where I live in Bloomfield was a chore, so I'm happy to be able to come here. It's a much easier commute. So, a couple of definitions. Astronomy, which is an ancient enterprise, is a descriptive activity. I have a science club that I'm part of and I run. People come to my house and we argue about these things. And I asked one of my friends last night, who's an astrophysicist, what's the difference between astronomy and astrophysics? And he said, astronomy is sort of like bird watching. You go into the forest and you see things and take pictures of them, count the number of each type, watch what they do. Eventually you get enough information that you can predict that the woodhatch is going to do certain things in a certain way at certain times of the year. But that enterprise of cataloging all the properties of birds is a lifetime's effort, and there's no time to dig into the details of why are the birds doing that? What are birds made of? How did they get here from ancient animals, their ancestors? So astronomers, just making observations, have collected an enormous amount of information about the universe. But it took until the invention in the early 1900s of new branches of science, principally relativity and quantum mechanics, so that we can talk about what's going on inside the sun that allows it to make the energy that illuminates our world. And that's the topic of astrophysics. And you can still get a degree at probably here and CU in Boulder and so forth. You can get either a degree in astronomy or astrophysics. The astrophysics is more about what are the processes that go on in stars and all the other things that are out there. Astronomers are focused on designing and building instruments and doing observations. So I want to make that distinction. Cosmology embraces the whole enterprise. What is the universe? What is it made of? How does it change over time? We'll talk a lot about that today. I call this class Modern Cosmology because of something I said a few minutes ago. I'm going to inform you about what's happening in the community of cosmologists and astrophysicists as I see items pop up. We're not just going to talk about what was going on 40 years ago. We're going to try to make this modern. So we talked about this. Quantum mechanics, I mentioned, which is the study of atomic and subatomic things. Without understanding that, we are stifled and we can't make much progress. Oh, you locked someone out? Yeah. Sorry. Hello, welcome.
Oh, thank you.
Yeah, find a seat, and we're a little, the way we laid the tables out, you might have to move around a little bit, because I created a problem here by putting my camera right in the middle of everything.
I can sit back here this way.
Well, okay, so wherever you come. So here, on this page, I'm pointing out that we will do some flashbacks, because some of the stuff I'll talk about, and then to fill in the details, we'll have to go backward and forward a little bit, just like science does. The science is a 2 steps forward, 1 step back kind of enterprise. So there's no single path that I can take through all the topics without creating confusion. Now, we might as well get out of the way some of the things that are so stupendously huge or so stupendously small that we have to agree now we will never really, we have no physical experience with things on this scale. For example, the speed of light. 300,000 kilometers per second. That's a big number. None of us have or ever will experience anything like that. But something to digest. How far light goes in a year? 6 trillion miles. A number far bigger than our solar system. We just have to accept the fact that none of us have experienced anything like that. In and around the Milky Way, if we took a little grain of couscous, said that's the size of, let's see, Earth, the sun is the size of a ping pong ball in comparison, and they would be 15 feet apart. There's lots of these things floating around, like analogies of how you can try to gather a sense of how big or small things are. The Voyager spacecraft, which the Voyagers were launched in 1976, I think, they're going fairly fast on a human scale, 38,000 miles per hour. It's taken since 1976, or 35 years. They've just reached the outer limits of our solar system. And we can tell that they've left our solar system because the sensors on the spacecraft are still working, and we can see that they are not under the influence of the sun so much anymore. They're out in intergalactic space. But that represents 17 light hours. So keep this in mind if we talk about how long it would take us to go to the nearest galaxy or star or something. The distance
question?
Sure.
On the top line there, for speed of light, it says 300,000 kilometers per hour, but you said per
Oh,
second.
per second, sure, thank you. Steve corrects me, correct, thank you. It's 300,000 kilometers per second. You know, this is what happens. I write stuff, and then I have to rely on the students to make it right. So, all of us have encountered CDs of music or video. Just, if our solar, let's see, on this, yes, if our solar system is the size of a CD, about 5 inches, the galaxy that we are in, the Milky Way, is the size of the United States. And we're just kind of an average, orbiting around an average star in an average galaxy. What is phenomenal, I'm going to skip a couple of these things, except Andromeda, 2.5 million light years away. That's our neighboring galaxy. Here's something they have to know. In the field of cosmology, the unit of measure is galaxies. If you look at the human body, if this was a conversation about medicine, we would talk about cells. Because that's how organs are made and so forth. Galaxies are the unit of measure. Not stars, but collections of stars. And a galaxy has, in a rough measure, 100 billion stars. Each galaxy has 100 billion stars. And there are groups of galaxies called clusters. You might have 10 or 100,000 galaxies in a cluster. And then there are superclusters. Overall, there appear to be about 100 billion galaxies in the universe, each with 100 billion stars. So now, finally, we're ready to start talking about questions. I want to encourage you to interrupt and let's have a conversation about these things. Here we go. If there are questions, this would be a good time to bring them up. If not, any time during our conversation is fine. I may not be able to answer your questions immediately. Sometimes I just make stuff up, but most of the time I'll go do some research. I usually will stay after class if you want to have a conversation. Actually, I should tell you another little background thing. Not only have I taught this at CSU, I just got back from the Middle East. I was invited to speak on a cruise ship that went from Dubai, in the United Arab Emirates, to Mumbai, India, because during the cruise, we witnessed the eclipse that occurred in that part of the world. That eclipse was not seen here in North America. And so we saw what's called an annular eclipse. That is, the moon's orbit is not a circle. It's an ellipse. And if the moon is a little farther away than normal, it appears a little smaller on the sky, and it doesn't quite cover the disk of the sun. So we saw an eclipse where the sun was blocked out except around the perimeter. So the so-called ring of fire. A very interesting picture was taken not far from where we witnessed the eclipse the day after Christmas, but in Oman, which is on the Arabian Peninsula. A professional photographer took a picture of the eclipse, and at that location, the eclipse occurred at sunrise. So the sun was red. And you've all seen that effect, where the sun on the horizon was red, and the moon was sitting on top of the sun, except there were two arcs of sunlight, red sunlight. And it looks like the devil is peeking over the horizon. So you might want to look for that on the internet. So anyway, I paid for my passage on the cruise by lecturing on the topics that we're going to discuss. Okay. So let's start with some history. I know this is hard to read, but you all will have access to all the lecture notes. What this shows from top to bottom is the range of years from 1500 to 2000.